everyone, my name is Katerina Galitskaya and today I'm joined by Daniel Faircloth, the CTO and one of the creators of Nullspace. I have already talked about Nullspace a lot in my tutorials, but today I wanted to dive a bit deeper into that and ask the person who actually wrote the solver. Hey Daniel, thanks a lot for joining me today.
Hey, Katerina, thanks for having me.
One question before we go into technical details. Really interested why it's called null space.
Yeah, uh, it's a bit of a math joke. In linear algebra, um, the null space is you know, uh, as a certain mathematical term that has consequence when you're solving systems of linear equations,
Hmm.
and to some extent, all computational physics solvers are ultimately solving a linear algebra problem. And at its heart, Nullspace, the company, is producing a software package that solves these linear algebra problems of grand scale very efficiently, very fast, and Nullspace as a mathematical concept plays in. So we thought it'd just be a cheeky little joke to name the company after this. Plus, there's a bit of a double meaning. We started from nothing, so the null,
Yeah.
and we're building something new. So you know,
Yeah,
so
was it
that's
was it hard to because it sounds really like catchy, because it's like short and nice sounding. Was it hard to come up with the name?
uh, honestly not as hard as I thought it would be. I was surprised
It
that
came
the name was
really
available.
naturally. Yeah.
Yeah. And that it aligns so well to kind of have this fun double meaning.
Yeah.
Plus it sounds better than
Yeah.
just an acronym or you know uh
Yeah, I agree. It's kind of more more human.
yeah, yeah,
Kind of. Yeah, so yeah, I agree that I like the name. It kind of sounds very natural and kind of like good to hear it. So I was working with the null space now for some time, and got some questions from my audience about the tool. So I think you are the best person to ask this question. So I will ask them.
okay.
First question is, I think that you can anticipate that is why we need the new tool. You said that when you worked with like in the beginning and the need arise for new tool, what was the need?
Yeah, a great question, and a very fair question that people would wonder why another simulation tool. And honestly, we were building the tool that we wished we had for the types of problems that we were being faced with. The existing tools are powerful, but they were designed in a different era, before accurate large scale solution techniques were really available or matured, before GPUs existed, before cloud computing, before Python became the language of engineering. So we saw an opportunity to rethink the whole workflow from the ground up, across all of these different aspects. Not initially, with the goal to replace the incumbents in the areas where they shine, but to give engineers another option that fits, how we actually work today, the types of problems that we need to be able to solve. And uh, there's a gap in the engineering space for large problems, particularly those with many excitations, that need to be solved accurately. Things like fast multipole and shooting bouncing ray, that you'll be exposed to when you kind of look across the landscape of solvers. Those techniques are fast, but they often, sacrifice too much accuracy.
Hmm.
And we were trying to design and analyze problems where we couldn't sacrifice that accuracy, but the problems were still really large scale. So how do we do that?
Yeah.
Um, you know, and we wanted to be able to take advantage of modern computing architectures, modern techniques, but really those modern techniques, had never made it out of academia, and they weren't made for and modified for real world problems. So figuring out how to do that to be able to address um, large scale phased arrays, large radar cross section
Hmm.
problems, or other kind of scattering problems. That was the gap that we saw and that we needed to fill, and that's what we've been doing.
Yeah. Yeah, I understand that. You use the word modern quite a lot, and also even in the description of null space, it says that it's modern method of moments. What's
Hmm.
modern about that?
Yeah, I think modern, in our case, means rethinking everything, from the ground up, from the algorithms to the hardware to the workflow for uh, present day computing environments, and to address, these problems that we just talked about that have been long avoided by engineers, and that avoidance is, I say avoided, but it's not really necessarily a choice by the designers themselves. It's a lack of previously existing capability to solve these
Hmm.
kind of problems. So we're combining, modern, accurate matrix compression algorithms that really function well on real world problems with GPU acceleration and high order physics formulations. So it's all built on a method of moments framework, which method of moments itself is not a new
Yeah.
technique, but building it from the ground up with all of these other things in mind is what
Mm.
makes it modern. And we're combining all of those technologies in the solver, with an end-to-end Python capability that allows users to have the most flexible workflow possible, um, to allow them to express their geometry in a way that legacy tools can't. And even our licensing model reflects the modern way people work. You work, maybe you're sitting at your laptop, but you have large, computational machines available. Some machines have GPUs, some don't. So our licenses are 100% floating all the time, and there are no paywalls just because you have a large machine with a lot of cores or with GPUs or anything like that. Um, we we like to joke, that Nullspace was built by engineers for engineers, so we're not trying to, do anything that, inhibits what an engineer needs to do to get their work done.
Yeah. Yeah, that's always the most frustrating things, right? That's like not related to engineering actually.
Right. Yeah.
You said about so large problems, and that is what like electrical large problem. That's the focus, right, of the software. And I also,
Right.
when tested the null space, I noticed that there is like different approach to that. Was that from the beginning the focus was of your work?
Yeah. We wanted to, um, we had that gap identified. We were
Hmm.
we were frustrated, struggling to design large phased arrays, or you know, a phased array with a multi-layered radome, and then you install that on a platform and you want to
Exactly.
simulate that, or you have a large scattering problem, you want to understand, the physics associated with some radar cross-section type of analysis. And these are problems where traditional finite element or time domain methods, or even traditional method of moments um, methods, they start gasping for air on normal computing resources.
Yeah, right.
And
But
we
for example, we can use something like this like shooting bounce and race solver, right?
Right. Yeah, and shooting bouncing ray is a great ray tracing method. There's the ANSYS has the SBR plus
Yeah.
solver add-on for HFSS, and that's a great technique for certain classes of problems, but it's fundamentally a high frequency asymptotic method, which
Yeah.
means that approximations to Maxwell's equations are built in, and so you're only ever getting an approximate answer.
Hmm.
And it works great when problems are electrically huge and maybe an approximation is acceptable. But when you're talking about large scale phased array coupling or coupling from one antenna to another on a platform, or antennas are in deep shadow regions from each other, but they
Hmm.
have a sensitive receiver, and it's very important to capture the full you know rigorous formulation of Maxwell's equations. Then you can't really use a technique like that, or you're at at best you're taking on a lot of risk, in your design process by doing that. So if you need, you know, a, a rigorous solution to the current distribution or coupling or anything like that, or if you're, then you want, you know, a solution like we're providing. If you're solving, say, RCS on a 737 at millimeter wave, something like SBR is really your only choice to date.
Yeah.
Although we're working on that. So
That's good to hear. That's good to hear. From my point of view, it's always like engineers always win when we have more options, right, to
mhm,
choose from, and
right.
also the like general development of the area also wins from them more companies and more developments working on with like developers working on that. So yeah, for me, it's only win-win that you work on that.
Yeah, we
What
think, competition is a good thing. So,
Yeah, exactly. Competition is a good thing. Was wondering about the Python. So you have really deep integration of Python and the workflow based on Python. And when you built it, I think the Python wasn't so popular as it is now with AI and everything. Like, why you decided to do it like that, or you already kind of saw it coming?
maybe a little bit of both. I don't certainly we, can't predict the future exactly the way it has played out, but we could see Python was taking over the engineering
Mm,
space, early early data science, it was already the dominant language. And then other domains. It's also very pragmatic. Um, lots of engineers use MATLAB, and so Python is a non-proprietary solution that,
mm,
has some parallels there as well. And then we wanted to provide users with uh, as I mentioned, a non-proprietary scripting language, and also free them from the restrictions of other solvers that basically have GUI only workflows,
mm-hmm.
because that's limiting, in some capacity. You're restricted basically to the workflow that the GUI designer has allowed you to pursue.
Right.
Whereas if you have, something like a deep Python integration, you can really do whatever you want to. I think others have pursued uh, Python integration, but it definitely feels like an afterthought. And I think
Yeah.
users can tell that sort of thing when it is sort of a bolt-on as opposed to a ground up sort of solution. And
Mm,
so, our approach has been, well, let's take the Python capability, let's build something that is very powerful and expose that to the users. And then we can build things on top of that powerful foundation to
mm-hmm.
streamline certain workflows and make things, a little faster here and there for, everyday activities, but the powerful capability is always there, and it stretches end to end, you know, from the throughout the workflow. And then, as we've seen, uh, particularly in the last couple years with the AI boom, Python is already the non-proprietary language of engineering, and so many other disciplines. And so we just thought that AI is going to integrate itself into engineering workflows. The language for that is predominantly going to be well, both the English language, as we've seen with LLMs, but then Python as well. And so just having that capability and really doubling down on that Python integration, I think
Mhm.
is long term a long term win for our users.
Yeah, absolutely. I really like the workflow when you kind of get into that. Maybe in the beginning it looks a bit intimidating, right? Because of the like Python, you have some coding, maybe you kind of not so familiar with that. But literally like you can make it as easy or as hard, like as deep, right, as you want. Kind of you can either go like some very basic surface level, or you can go very deep and like control everything that you want. So it's also like this flexibility really kind of, I really like it.
Yeah, well, thanks. I'm that's been the
Feedback for
goal.
you.
Yeah, we even on the GUI side, you can I've used commercial and open source tools where
Yeah,
you basically need a PhD just to figure out how to draw a rectangle.
right, right.
And so from that perspective, there being some Python code exposed to the users is not a big deal. And once you realize the capabilities that affords you
Mm,
as a designer, it's definitely a win. Um, the physics is already complicated enough,
right.
so the interface, whether you're using the Nullspace prep GUI or you're using the Python API, we've tried to strike the best balance of both worlds, I guess, in terms of flexibility, but usability. And really, this is a never-ending journey. So we're listening to the customers and trying to make additional improvements to the usability and create capabilities, where those users feel like it'll streamline their workflows, um and we'll see it continue to improve, I think.
Yeah, for sure. What about the improvements? What do you like? What do you feel like? Which kind of way are you going? Is it something like AI integration, or is it like more just into like improving the tool itself?
There's both. I think we started off focused on solving large problems as fast as possible, without sacrificing accuracy.
Yeah,
And that need is always going to exist.
right.
It's a user's hunger for what constitutes large and what constitutes fast. I've learned is really insatiable.
Right.
My own self included. So we're continuing to work on new and better techniques to solve these large problems, large practical problems, without compromising accuracy. And I think the AI piece of it is certainly going to come into play. There's a we're seeing it in the engineering community already with surrogate modeling and design optimization and things like
Mm,
that. But I think long term across the engineering ecosystem, there's a bigger shift coming, where AI can interpret the results. AI can suggest design modifications. If you're so much so in the software engineering world, there are already talk about AI from the perspective of like, you take the view of a product manager,
Hmm.
and now, you know, we're seeing an evolution where in the engineering space, you can for for physics, different physics domains, like you can take a similar view, and we can imagine someday that your your AI enabled engineering software is actually seeing the CAD and then seeing your S parameters, for example,
Hmm.
and making some design suggestion based on that, or even going further, maybe you let the AI take the wheel and it's actually doing some autonomous design capability, and you're guiding
You
it.
mean some like optimization, like based on like AI, some algorithms, like for example, like topology optimization or something? Because I've heard
Exactly.
that's already kind of exists. I don't know. Is it pure AI or is it just like just some algorithm? But like, well, it's basically doing engineering job, right? It finds the best solution, kind of best topology, for example, for some like PCB antennas.
Right. Yeah, you see a lot of topology optimization even um, before the large language model kind
Yeah.
of explosion that has happened, um, especially in the mechanical engineering world. There's a
Mm,
lot of topology optimization. And then in the EM world, there's been a lot of effort, sort of in like the pixelated antenna designs,
mm,
and some efforts that are, looking at how you can optimize like Boolean tree or trees of, CAD operations to include Booleans and things like that.
mm-hmm,
And if you are able to now take those capabilities and express them in a way that, say a large language model can interpret
mm-hmm.
those results, um, I think that's going to open up a lot of landscape for the engineering design discipline, really
Yeah.
across all physics domains, not just EM.
Yeah, I think it's very interesting. But I really like. I presume it so that it will be just kind of in parallel with the engineer. So it's like it's always kind of like in the helping role, right? Not replacing, so we don't lose our jobs, at least.
Right. Yeah, and people talked about this even maybe 15 or 20 years ago when global optimization, things like genetic algorithms and particle swarm optimization, those algorithms were having uh experiencing, their moment in the limelight, and people were talking about, oh, this can completely replace, an
Yeah,
antenna designer. And really, it's not that it could replace an antenna designer, but it was a new capability. So if you were
mm,
already a good antenna designer, this new capability was going to make you even better.
yeah, right.
And I think, you know, we're going to see a similar sort of thing with as large language model technology gets better integrated with high fidelity engineering tools,
Mm.
that we'll see a similar sort of thing. A single antenna engineer is going to become a super engineer, instead of
Right. I like the
yeah.
title. I would like to be a super antenna engineer.
Yeah, me too.
Okay, that's very nice, very interesting approach. I share it. I think that's probably what will come from that. The last question that I have for you is, what is the best place to start with Nullspace if somebody from my audience want to try or want to learn maybe more about that after watching all my tutorials as well?
Yeah, and thank you for those great tutorials. Yeah, I think the best place to start is is with our website, nullspaceinc.com. Uh, you can go there to contact us to, get set up with a trial or,
Mm,
just have a conversation about what kind of problems that you're interested in. And then,
right.
of course, we've got a YouTube channel. We're active on LinkedIn. We've got an academic program as well, so universities can get involved. And then, once you get kind of plugged in, there's a user forum that's active, and I think that's probably the best places to start.
Right. That's the community is very important, right? People helping people. So
Yeah, bringing it back to the beginning. Yeah,
yeah,
you
exactly.
need the
I
people.
like that.
So,
That's the best.
yeah,
When I was a student, I always like asked the kind of these questions on the forums, like how to do this, like about the simulations, and people helped. So I think that's the best, better than to ask AI.
yeah, that's right. Yeah, we gotta
Okay.
keep helping each other out.
Yeah, exactly. Thank you very much, Daniel, for your time. That was very interesting, and I hope that my audience really liked it as well.
Yeah, thank you. I appreciate your time as well.
Okay, see you later. Bye bye.
All right, see ya.